Hello students. Before I start with the today's topic, let me revise the few points which we learned in the study class. So we started our discussion from the definition of filter, basically which is a network compromising of the passive resistor and capacitors. You may include the active components like op-amp also. And then we discussed the types of filters. They are analog filters and digital filters. So we know what are the types of analog filters. They are nothing but low pass filter, high pass filter, band pass filter and band stop or band reject filter. And then the most important part of this digital signal processing is to study and understand the design part of the digital filters. So before we understand how to design or implement these digital filter types, we are able to understand the basic definition of digital filters and their classification, and as well as the key difference between the types of the digital filters. So as we discussed in the yesterday class, we have got two types of digital filters. They are namely FIR and IIR filters, and they are classified based on the duration or the period of the impulse response, right? And the impulse response of any system is nothing but it is the response or output of the system when the input is the impulse function, right? And based on the duration of the impulse response for the given dynamic system, we classify the filter into IIR and FIR. So IIR filter is basically refers to what? It is infinite impulse response, and FIR stands for it is finite impulse response. And then we discussed the infinite impulse response is characterized by its feedback. That's why it is also known as the recursive type filter. IIR filter is a recursive type. So there is a feedback, and due to the feedback, the present output is not only depends upon the present input and past input, it also depends on the past output also. And when it comes to FIR filter, it stands for finite impulse response, and it does not have the feedback. It doesn't have the feedback. That's why the present output depends on only the present and past input, not the past output. So that's why the FIR filter is a non-recursive type filter. And if you take the transfer function of IIR filter, it has got both numerator and denominator. So numerator corresponds to the zeros and denominator corresponds to the poles. So IIR filter is also known as the pole zero filter. But whereas if you take the FIR filter, it has only the numerator polynomial. The transfer function has only numerator polynomial, and in the numerator we have only the zeros, right? So that's why the FIR filter is also known as all zero filter. We don't have a poles because the denominator polynomial is absent in the transfer function of the FIR filter. That you have to understand very well. And then we discussed the linear phase characteristics, right? When it comes to FIR filter, which has a linear phase characteristics, but in case of IIR filter, it does not have the linear phase characteristics. And one more important point you have to remember is when it comes to stability, the FIR filter is more stable compared to IIR filter. But when it comes to design part, the IIR filters are very similar to your analog filters. in terms of their design, right? So this is the few topics, I can say the few points we studied in the previous class. And in the today's class, I will start my discussion with a very important one for your examination point of view, that is the implementation or realization of IIR filters in direct form 1 and direct form 2, right? So here we have two types of realization. One is direct form 1 and direct form 2. They are very simple. Only thing you have to remember, what is the transfer function of the IIR filter, right? So the transfer function of any filter can be obtained if you know its differential equation. What is that differential equation? It is the equation that relates the input and output of the LTI system. Most of the time the filter also behaves as the LTI system only. So here I will start my discussion with the direct form 1 and direct form 2 realization, right? So I will start with the direct form 1. So for both direct form 1 as well as direct form 2, so let me start the transfer function of the IIR filter, right? So if I take the LTI system, so this is my LTI system, or you can consider as the filter which is having the impulse response h of n, and its transfer function is what? H of z. H of n is what? Impulse response. So the response of this filter is y of n when the input is x of n, right? And the transfer function h of z, which is the z transform of impulse response h of n, and which is given by ratio of the z transform of the output, which is y of z, and the z transform of the input x of n, which is x of z, right? And the numerator polynomial contains only a zeros, so which is given by summation k is equal to 0 to m, and the numerator coefficients are given by what? bk, and here it is z raised to minus k, divided by the denominator polynomial is given by 1 plus, because it has a feedback, 1 plus summation. So here I will write k is equal to 1 to capital N, and here it is ak into z raised to minus k, right? So this is the transfer function of the IIR filter h of z in terms of the numerator coefficient as well as denominator coefficient, right? So to implement or realize this IIR filter, we need the equation in terms of the output, input as well as numerator and denominator coefficient in time domain, right? So how to modify this transfer function into a time domain equation? So for that, so just perform the cross multiplication here. So I will do the cross multiplication here. I will do the cross multiplication, so that what I will get is, so I will write like this: 1 plus summation k is equal to 1 to capital N, and here it is ak z raised to minus k, and here it is y of z. So here we get y of z is equal to, if I multiply this one, this numerator polynomial with x of z, so what you will get is k is equal to 0 to capital M bk, and here it is z raised to minus k, which is multiplied by x of z, right? So only have to simplify the left hand side of this equation. So what I will do now is I will multiply this y of z with the inner terms. So here I will get y of z plus summation k is equal to 1 to n ak z raised to minus k, which is multiplied by y of z, which is equal to, keep the right hand part of this equation as it is, k is equal to 0 to m bk z raised to minus k into x of z, right? So once you perform the cross multiplication, in order to have the differential equation in time domain, what you have to do is you have to simply perform the inverse z transform on both LHS as well as RHS. So if I take the inverse z transform of y of z, ultimately what we get is we will get y of n plus summation I will keep as it is. So k is equal to 1 to capital N. So this is the denominator coefficient ak. So I will not alter, I will keep as it is ak. So see here, so it is z raised to minus k y of z. So if you take the inverse z transform of this one, what you will get in the time domain? So you will get y of n minus k. Hope you are aware of this one, right? So what is a z transform, what is inverse z transform, how to do that, right? Hope you have studied in your previous semester. I will not repeat this one again, right? So when it comes to right hand side now, so I will keep summation term as it is, k is equal to 0 to m. Denominator coefficient I will keep as it is. So similar to this one, so can you tell me what is the z transform of inverse z of this one? So it is nothing but x of n minus k, right? So what I want is, I just want to write the equation for y of n, right? So I will keep y of n, only y of n in the LHS side, and this one I will write RHS part I will write first. So that is k is equal to 0 to m, and here it is bk x of n minus k. Now I will take this term to the right side. So it will be minus summation k is equal to 1 to n, and here it is ak into y of n minus k, right? So this is a very important equation which you can use to implement or realize the direct form 1 for IIR filter, right? So here bk and ak, they are real coefficients which are namely considered as numerator and denominator polynomials, right? And this y of n is the weighted sum of, you can observe here, right? The weighted sum of the past input, the present input, the past input. How you will get present input? If you substitute k is equal to 0 here, so you will get only x of n. And if you substitute k is equal to 1, 2, so on up to m, what you will get? X of n minus 1, 2, 3, so on. So this term is comprising of x of n as well as the past inputs. So similarly here, if you substitute k is equal to 1 here, you will get n minus 1. So this is the past output. So here output y of n is the weighted sum of the present and past input as well as the past output, right? So if you know this time domain equation, you can easily realize the direct form 1 structure for IIR filter. So let me start the structure, the direct form 1 structure, right? So here one side I will write x of n, one side I will write x of n. So here I will write x of n, and here I will write my y of n. So this is the first step. Here you write x of n, and here we write y of n, right? So here first let me consider this one. So here substitute k is equal to 0. So if you substitute k is equal to 0, what you will get? B naught is there. So b 0 and k is equal to 0 means you will get x of n. So now this x of n is scaled by some real coefficient b naught. So this x of n is now scaled by what? B naught. Is that clear? Next, substitute k is equal to 1 now. If you substitute k is equal to 1, so what you will get? You will get b1 multiplied with what? X of n minus 1. So what is this x of n minus 1? It is 1 unit delay of x of n. So how to get that? So I have to introduce a delay element here. What is that delay element? Delay element is z raised to minus 1. So if you take the delay element at this point, you will get x of n minus 1. So in the exam or during your practice, don't write this x of n minus 1. So just for the understanding first time, so I am writing x of n minus 1, right? And this x of n minus 1 has to be scaled by which coefficient? b1. So this b1 here you write. Since here it is summation, each the scaled factors you have to add every time, right? Similarly, next, if you substitute k is equal to 2, you will get x of n minus 2. So how to get x of n minus 2? You have to add one more delay element to x of n minus 1, so that you will get x of n minus 2, and this x of n minus 2 is scaled by what? b2, because you are substituting k is equal to 2. So here you will get b2, and again you have to add. So you have to add all these things, right? So it goes till m. So what I will do is, it goes what? Z raised to minus 1. How many? You have to consider m number of z raised to minus 1 delay elements. And finally, so what is this one? So this is the mth real coefficient, right? And here you have to add. So this is the one part, right? Again here summation is there for y of n minus k, right? Y of n minus k. Since IIR has feedback, so it has to go from output to what? Towards input. So I will take one more summation here, and here we don't have k is equal to 0. It will start from what? It started from 1. So I will simply write here like this, or you can write 1. There is nothing wrong, right? After that, substitute k is equal to 1. When you substitute k is equal to 1, so here it is a1. What you will get? a1 and a1 y of n minus 1. So what is this y of n minus 1? It is 1 unit delayed, right? So here it is y of n. How to get y of n minus 1? So here I have to write z raised to minus 1, and this point you will get y of n minus 1, and this y of n minus 1 has to scale by what? Here it is minus, so this minus, and here it is a1. So here you have to write minus a1. Here you have to be very careful. It is not plus a1, it is minus a1. So again I have to consider adder because of summation. Similarly, substitute k is equal to 2 by taking one more delay element, and again it is scaled by what? Now minus a2. Again you have to consider summation here. And similarly so on up to, if I take delay element, what you will get here? So this can be, this could be your y of n minus capital N, and here it could be minus an, and here it is, right? And both are connected. So this is the direct form 1 realization of IIR filter, right? So hope this concept is clear. So in the next video we'll discuss the direct form 2 realization of IIR filter, which is the continued part of this part, that is direct form 1, right? So hope it is clear. We'll discuss the direct form 2 realization in the next video.